This call was.
All right, so today we're going to start with some complex numbers. Okay. All right, so why do we need complex numbers? Well, kind of for the same reason we need fractions and decimals. Complex numbers occur from counting numbers. So what's our counting numbers? Well, obviously our counting numbers are 1, 2, 3, etc. Just that full screen. Okay. Counting numbers are 1, 2, 3. I don't know if you've ever looked at counting numbers before, but the Roman numerals, they use 1, they use 2, they use 3. It gets a bit more complicated after that, obviously, with the IVs and all that. But if you ever think about our numbers, 1, very similar actually. 1 is 1. 2, how do you do this again? You use 2 lines here, and 3, you use 3 lines here. And then you just, you connect. They're formed in quite a similar way to the way, so that is the Arabic form of numbers. Anyway, that's just a side note. But yeah, so counting numbers do create complex numbers, and before that, they created numbers that weren't counting numbers. So the Greeks probably, maybe the Egyptians as well, were the first that came across this. So a very simple example is Pythagoras. So if we have if you just count out 5 units that way and count 3 units that way in a right angle triangle, what you get on this side is no longer a counting number. Because you would square 3 and square 5, and then you get a square root of 34, which is no longer a normal counting number. So we need to then delve into fractions, numbers like these, surds, so and irrational numbers, and then we need to include some complex numbers, which is the square root of a negative number. But let's just look at how counting numbers form each of those using algebra. Okay, so this is a very simple algebraic equation. The solution is a counting number, so there's no problem there. X is equal to 5, and it's from the set of natural numbers, which are all the counting numbers. Let's look at how we get a number that's not a natural number. So our first delve into non-counting numbers would be if you have an equation like this. The solution to this equation must be -2, which is our first delve into integers, which of course is the set z. Okay, so that we've noticed that, okay, so that's counting numbers work this way on the number line, and now they have to work also before 0 on the number line. So that's what mathematicians throughout the years started to notice. And also, if we move into the realm of fractions, the answer to this would be, well, let's keep it positive for a second, is a half. Doesn't matter, could be negative either. And that moves us into the realm of quotient or rational numbers, which Q is our symbol. So that's some sort of division. All right, so that means the in-between numbers between our points are starting to be taken care of when we don't have full numbers. And then if we want to get something that's beyond that, we once again, so notice the way I'm only using counting numbers here, and our solution then in this case would be x is equal to plus or minus the square root of 5, which brings us into the realm of irrational and real numbers. So real numbers is basically any number that can be placed on our number line here. So it's a real number, also an irrational number. We just stick with real. All right, and then our final one, and it is the last one that we can form using counting numbers. If we have x squared equals +1, that means x is equal to plus or minus the square root of -1. And that has been formed just from counting numbers, normal counting numbers. And what was come up with is a complex number. a number that if you put it into the calculator, which only deals with real numbers, well, most calculators, some calculators now deal with complex numbers, but you do no longer get something on this number line. You get something with I in it, because the square root of -1 is I. So the answer to this equation is plus or minus I. No longer. So the square root of -1 is our delve into complex numbers. Can we get any more than this then? So using counting numbers in algebra and finding solutions? No, we don't go any further. There is no other way using counting numbers to get any other type of number. And you can probably, that makes logical sense because you've exhausted our operations here. So complex numbers is where it ends. And this is kind of the fundamental theorem of algebra, which maybe you had a little look at in chapter 5. Any polynomial with complex coefficients, so if your x squared is a coefficient of a complex number, it will only have complex roots, as in it can't get any more than that. That's the, so if it has coefficients that are natural numbers, you can get complex roots. If you have integers, you can get complex roots, or you can get real roots, or you can get irrational roots, but you can't get anything more than complex roots. And that's kind of the fundamental theorem of algebra. You can't get any further than complex roots. All right, so let's have a little look at how we deal with complex numbers and what they look like. So maybe perhaps you've come across something called an Argand diagram, where we have a real number line here. That's real, that's our normal number line from year 7 and whatever. That's just 1, 2, 3, -1, -2, and that's the one we've always used, and I use currently with my year 7s. And then we have a new number line, which is the imaginary one. I, 2i, 3i. So actually numbers are 2-dimensional, not 1-dimensional. Okay. Anymore. They have 2 dimensions to them. They have a real part and an imaginary part. So if we write a complex number, usually z is used. You can put a little line through the z if you want. The only reason for that line through the z is to distinguish it from a 2, probably. So if you want to use that always when you use complex numbers, you can. And you see that they are written maybe x plus I y or a plus I b. It's a bit like a surd. A surd can be written 2 plus root 3. There is no way to combine this into one number, into one written number. Like, it's not 2 root 3, that would be 2 times root 3. It is one number, but there's no way of writing it other than separating its parts like that. It's a bit like, can you add an x and a y? No, it is just x plus y. It's not anything more than that. So this is our standard form of a complex number. Let's rewrite it down here. Now, this x part is its real part, the real part of the complex number. The real part is z, so you sometimes use REZ for short. And the y part is then the imaginary part. Now, why do they use -1? Why don't they use -2 or -3 or -4 as I? Well, if you think about it, 1 is a factor of everything, so it's easy, and that's the only reason. So it could be the square root of any negative number. They could have made it, but they made it 1 because it's a factor. So if you have the square root of -3, for example, that can just be written the square root of -1 times the square root of 3, which then, it's a factor of 3, the prime, even a prime number, which is fine. So that would be written I root 3 or something like that. Okay, so that would be the I part, and the imaginary part of this would be just root 3. Now, for your entire existence so far, you've been dealing with complex numbers, but you didn't really know, in a way. Every complex number is, for instance, the number 5, any normal counting number, is technically a complex number. That can be written z is equal to 5 plus 0i, or I0. Usually you put the number first. It just has no, it's only on the real number line. But it does have a complex part to it. It just is nothing at the moment. So these are called purely real numbers. If I have a complex number such as just 3i, that is a purely imaginary number. Okay. Now these numbers do come up in algebra and in life. The square root of a negative number just comes up a lot, especially when we're dealing with polynomials, which you may have noticed. So you can talk about the zeros of a polynomial, and they can be imaginary. And that's what we're going to look at in a minute. All right. Do stop me if you have any questions. Otherwise, I'm just going to keep talking. So, most people in life don't even come across complex numbers. Only people who start to study maths at a higher level come across complex numbers. So most people in their life are restricted and don't get to enter the wonderful world of imaginary. Imaginary is a poor number, or a poor name, because they're actually, they're there, they exist, because the square root of a negative number happens. So therefore, imaginary is probably a poor term. Complex numbers is a far better term. They're just a little bit more difficult. Okay, so let's start to look at some polynomials. Let's consider a simple one, x squared plus 5x plus 6. Let's let it equal 0. All right. There's a number of ways. Focus, camera, focus. There's a number of ways that we can solve this. We could factorize, we could complete the square, or we could use the quadratic formula. Now we already know the answer to this, so hopefully you know it's -3, -2 from a simple factorization. But it's interesting that if we do use the quadratic formula to find its roots, you get -5 plus or minus 25b squared, 25, take away 4ac, so that's 4 times, 20, take away 24, all over 2 times a, which is just 2. Even though you know that what comes out are whole numbers and they're very simple, we have a surd here in the formula even. And this is kind of similar to the cubic formula, which actually has complex numbers in it. And that's why you never get shared the cubic formula. Maybe we can look it up at the end of the lesson, but it is an absolute ginormous formula, but it's usable. But it does include complex numbers, the same way that the quadratic formula includes surds. Now, when we work this out, we get -5 plus or minus the square root of 1, which is 1. Okay. There's only 2 answers to this. -5 plus.
So what happened to the divided by 2? Okay.
Yeah, thank you. So you get -5 plus 1, or -5 minus 1. And that gives us a -3 or a -2 answer. Now, if we think about this, and what we've done here, if we have a -5 and a 2, that's the axis of symmetry, minus b over 2a. And what they're doing is that either side of that, they're talking about an even distance either side. So they go plus the same distance, minus the same difference, and that's how we get our two roots to this equation. If you ever thought about the quadratic formula even more, because you know that minus b over 2a is the axis of symmetry, so it splits it. And you would have even side, okay, my diagram is not brilliant, but either side is an equidistant from that. And that's why we do plus one side and minus the other side of it, and they're in between is its little friend here. Now the cubic formula does exist. It's going to take me too long to write it out. I would definitely make a little note in your notes to look it up.
And with the cubic formula, sir, it's not. I guess it's not plus or minus.
Oh, you're online there. If you want to take 2 seconds to actually literally look it up and have a look at it, you can see that it's going to be more than just plus and minus. There is part of it that's plus and minus. But the interesting thing is it's got a square root of a minus number in it, which is, of course, in the realm of complexity, which means that cubic equations often have their zeros as complex numbers, which you hopefully noticed as you did your polynomials.
Yeah, that's pretty long.
Yeah, it's pretty messy. If you've looked it up, the cubic formulas.
Wait, yeah, I'm looking at it now, but sir, so if you were to put every single input every variable that's in the equation, it would spit out what kind of answer would it?
Yeah, give you the roots. Same as this gives you the roots. Yeah, you get two
x-intercepts, right?
You get 3 answers for x out of it. But it's not on the course. It's not on the course, and it's not necessary for you to know, because with the help of technology, you can find one root, and if the other two are complex, there's no issue. So if I'll get into this in a second, but if your cubic equation is whatever, you can graph that. You'll get this root here, and once you have one root, you should be well able to find the other two zeros using division. Maybe you came across that, maybe you didn't, but we'll get to that in a minute.
So isn't also like if you have a complex root, then you're gonna have, I forget what they call it. It's basically, it's not like the reciprocal, but
conjugate, yeah.
Conjugate, yeah.
Yeah, you'll have so that's from the plus minus. So you can even see it happening here. Because what happens with a cubic equation, it generally, well, it is a quadratic equation multiplied by a linear equation. So what happens then is you might have the answer to the linear equation as x equals 1 from here. And we'll get to this in a minute, but it's a good question. You can see then that the other one would be a plus minus because it's quadratic.
Yeah.
So it's a plus minus but it will be a lot of them, especially if they're off the axis, like my diagram here. These are going to be complex zeros because they don't cross. They don't cross. If your cubic equation crosses at 3 points, hey, they're all real, fantastic. But if you have one like this, which most of them are, your zeros are going to be off the real axis, which means they're going to be imaginary. Okay. So, and that comes from the fact that, and then there's still going to be some kind of axis of symmetry, and still going to be like 2 imaginary floating up here roots, but they're going to be plus minus either side of an axis of symmetry. Okay. Like something on the Fibonacci. I don't know if we want to delve into that. I have a side note on the Fibonacci, which is interesting. The Fibonacci formula is another example of where a formula contains irrationality and surds, yet the numbers that come out of the formula are positive whole numbers, because we know the Fibonacci series is 1, 1, 2, 3, 5, 8. So hopefully you know that 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 5 is 8. So a simple writing of the rule Fibonacci formula would be to get a term, you get the previous 2 terms and you add them together. Okay, that's it. That would be the rule of the formula. But to get the actual formula then is an absolute, the Fibonacci formula is 1 plus root 5 n minus 1 minus root 5 n all over 2 to the power of n root 5. That is the Fibonacci formula to get any particular term in the Fibonacci sequence. And see the way it contains surds, yet all the numbers you will ever churn out of it will be positive whole numbers. Similar to the way the cubic formula contains complex numbers, yet you don't always get complex numbers out of it, because you can get 3 real roots no problem sometimes. So that is the Fibonacci formula. The root 5, you may ask, is got something to do with the golden ratio. And if you want to have a little delve into that, you can, but it is just a side note for the moment. But it uses irrational forms of numbers to form counting numbers. So you just look at the links between counting numbers and irrational, complex, surds, everything. So yeah, that's why we need complex numbers. All right, let's look at our, sorry, a new page for this. Let's look at 2 polynomials that are quite simple. X squared plus 5x plus 6 equal to 0, the one we just dealt with, and x squared plus 2x plus 4 equal to 0. Okay, so 2 relatively simple quadratics. Let's look at sum and product of the roots. Okay, so alpha plus beta from this. Rigel, what's alpha plus beta on this one?
Minus b over a.
Boom. So it'll be minus 5 over 1. So just minus 5. And alpha beta. So remember, alpha plus beta is minus b over a. And alpha beta then is c over a. Am I correct? I hope I am. C over a, which is 6. And we can do the same for this one then, based off that. Alpha plus beta, the sum of the roots is going to be minus 2. So minus 2 over 1. And alpha beta is 4. Yeah, okay. So we have sum and product of roots. We know what they are. Now, if we go to solve these, there's no problem here. We solve this one. We get x is equal to minus 2 and x is equal to minus 3, which we just did using the quadratic formula. However, if we solve this bad boy, it's not quite the same. Let's solve it using difference of 2, not difference of 2 squares, completing the square first. Okay, let's do x. I think it's x plus 1 to be squared. And what's going to be outside here?
Plus 3.
Plus 3, so yeah. So remember, x plus 1 to be squared, on a side note, which I'll just put here. X plus 1 to be squared is, you need to know how to complete the squares. Di and Dustin, if you're not sure, I think you're okay on it, but just in case, is x squared plus 2x plus 1 when I square it out. Now, I've added 1 when I do this, because this 1 has been added. It was x squared plus 2x, which means I have to subtract a 1, and then the plus 4 is still there. So I've added 1 in here, from here. And then I need to subtract it to balance it. And then if I subtract it, like I just said, I have plus 3 here instead of 4 plus 1. Now, if I want to sketch that, well, the parent function is just x squared, which would be just a nice little u here. It would be moved up 3 with a vertical translation here, up 3, and moved to the left 1, won't it, with the plus 1 attached to the x here. So I think it's going to be something like up 3 over 1. So the vertex is going to be here, maybe, at minus 1, 3, okay? So it's going to be something like that. And it's going to go through 4 here. So maybe that's a sketch of that. Now we can see that the roots of this equation don't exist. They're not on the real number line, are they? No.
Wait, sir?
Yes, did I?
I understand the complete square form, but I kind of forgot why you added 4 for when you did added 4 at the top. No.
In the equation.
Beneath?
Yeah, I know, it's the 4. It's the same 4.
Oh, so okay, right. So you got -1 for factorizing x squared plus 2x, right? Because 1 times 1 is minus.
X plus 1 squared is this. X plus 1 squared is this, which I'm trying to do complete a square. So x plus 1 squared is this, which means I've put in an additional 1 when I've done it. So I need to subtract a 1 to balance the equation. So you can't just add a 1 in.
Yeah, to balance it. Right.
Balance it. And that's but the 4 is still there. The 4 just continued on down there, and then they combined.
Okay, yeah.
Okay. So this drawing of it didn't quite get us the roots. So if we go to the formula, or we can use this. If you want to do the formula, and I'll try and you can find the roots this way. Either way, you would get. Well, let's do it using the roots instead. We know how to use the formula. Let's just make sure we can do it this way as well. Equals -3 then, so you can already see our problem here. I'm solving this, subtracting 3 from both sides. It's creating a negative number, square root. So if I square root both sides at the same time, I'm going to be left with, well, the squares cancel here. So your x plus 1 is equal to the square root of -3. Now, without knowledge of complex numbers, you perhaps would just give up here. And you would stop, because that's not real. But there's imaginary roots, or complex roots. I should stop saying imaginary. I don't like that word. Plus or minus, of course. Bringing over, subtracting the 1 from both sides, you get -1 plus or minus the square root of -3. Now let's just change that into a complex number, now that we know how. That root -3 is, side note, root -3 is root -1 times root 3, and root -1 is our I, so it's I root 3, or root 3 I. Either way, it's fine to write it. Usually you put the I last.
So how'd you get -3? I thought it was +3.
Moved it over to the other side.
Yeah, I'm solving it, but I +3, subtract 3 from both sides.
Okay,
Okay. All right, so my complex roots are 1 plus and minus root 3i from here. Root minus root 3 is root 3.
Sir, is I always root -1? Or
Yes.
is it...
I
Okay.
is always the square root of -1. Always. Okay, for the reason that I said at the start, it's because 1 is a product or a factor of everything. That's why they use -1. If they started using -2, it doesn't go into 3, for example. So you'd have to have a half I, and that's weird. So 1 goes into everything. That's why they use it. So that is the biggest note of all. I is equal to the square root of -1 always. And I squared then is equal to
-1.
-1. Yeah. I cubed
1. Or sorry. Negative.
Negative root -1?
Yeah, square root of -1.
It's -1 times I. Negative I. I cubed splits up into I squared times I. I squared is -1 times I. So -1 times I is just -I. Or you could have negative square root -1, which is a bit messy. But -I is usually the way it's written. I to the 4 then. Well, it's I squared times I squared. This is I to the 4. This is new. Which I squared is -1. Multiplied by -1, which is going to be a +1. Repeating pattern then. I5 is starting again. It's 1 from I4 times I, which is square root of -1, which is just I. You can just say I. So this, remember, are interchangeable. Usually, if you have the square root of -1, you don't leave it like that. You put I in, because I equals I. So your rotation of these is the same. I to the 6 then, if you multiply it again, you can do it out, it's -1.
So sir, you would never really use
this?
You would never use it past I to the power 4, right?
You would, yep.
Oh, you would? Wait,
Yeah.
it just repeats.
It just repeats. So you just have to work out what's the product. Is it a factor of 4? Is it not 4? Is it a factor of 4? Is it a factor of 3? Is it a factor of 2? And what in the rotation it comes. So you have to work out that logically. The easiest thing to do is to split it up. You know that every I4 is just 1. So I8, I12, I to the power of 16 is 1. And then you can work it off that. So if you have I to the power of 18, not 8, I to the power of 18, well, I know I to the 16 times I to the squared is I to the 18. I to the 16 is 1. Because every 4, it goes back to 1. Multiplied by I squared, well, I squared we have here is minus 1. So I to the 18 is just minus 1. Now, we will do a full unit on complex numbers. There's not that much in the polynomials. We're just introducing it as a general thing as zeros to a polynomial, imaginary zeros, which was towards the end of that chapter, I think. But yeah, you will have to deal with these, but not really until you get to the complex numbers unit in full. But it's good to have a little note, maybe have a note of this, and then just say it repeats every 4. You can see. All right. Now, let's get back to the problem that was in hand, where we got slightly off track there. That's okay. Questions. We have found these two as our roots or zeros of our quadratic, which, if you remember from up here, was let's just move this up here so we're on the same page. The roots we found were minus 1 plus or minus the square root of 3i. Now, we had a sum and product of roots, but our roots are complex. Do they fit when I add them and multiply them that I get counting numbers? Well, let's try it. Let's add them. Minus 1 plus root 3i, and then plus minus 1 minus root 3i. You happy with that? That's alpha plus beta for this one. Now remember, we had these roots because we went through it and got them here. Now, that'll be minus 1 plus root 3i plus minus 1, which is minus 1, plus minus 3, which is minus root 3i, okay? Plus root 3i minus root 3i, well, it's the same thing, adding and subtracting, and we're left with a negative 2. Hurrah! The same.
So didn't you have to multiply square root 3i to the whole parentheses to get rid of it?
It just goes
Where
with
do I
that.
have to do that? There's no root 3i outside.
Oh, I didn't see the plus sign. It's a bit blurry, sorry.
Okay. All right, and then I do alpha beta, which is minus 1 plus root 3i and minus 1 minus root 3i. So it's a bit messy now, but we'll just do it. I'm hoping to get 4. I'm hoping to get 4. At the moment, it doesn't look too promising. But this is the difference of 2 squares, so there's going to be some things cancelling out. Let's look. Minus 1 times minus 1 is 1. Minus 1 times minus 3i is plus root 3i, because it's a minus times a minus. Okay, that's the minus 1 done. Plus root 3i times minus 1 is minus root 3i. It's it, just change the sign. And the last term then is going to be root 3 minus, plus times a minus, root 3 times root 3, which is root 9, I squared. All right. That cancels with that. Again, sweet. Now we've got 1 minus root 9i squared. First of all, we know what root 9 is, don't we? That's just 3. 3i squared. We also know what I squared is.
Negative 1.
It's minus 1 now. So it is 1 minus 3 times minus 1. Minus 3 times minus 1 is plus 3. Okay, and you can obviously, when you get into the hang of these, that'll be a lot quicker a process because you could probably do it from here, but it is 4. So we have proven that the sum and product of roots holds even when the roots are complex, which is cool. Now, that's as much delving into complex numbers we need to do for polynomials. So polynomials and functions is the key here, but we just need a little background in our complex numbers, which hopefully that solved a few of your complex questions. But let's talk about polynomials now. All right, Dustin, what's a polynomial?
A polynomial is a graph that's that has an x value, like an x to the power of 1 or an x to the power of 2 or greater than that.
Okay, it's got x in it. Does anyone have a better definition of polynomials?
A function that has x to the degree of 3.
That's a type. That's a very specific type of polynomial, yeah. That's a cubic one.
Cubic, yeah. I think a function has 3 x-intercepts.
3 x's? That's the 3 x's?
It can be like x to the n, I guess.
Yeah, so would it be okay if I said like it has 3, if you were to graph it, it would have 3 x-intercepts?
No, you're being very specific there, but you're specifically linking it to a cubic polynomial, which, yes, a lot of the chapter was on cubic polynomials.
Okay, yeah.
But there's linear polynomials, there's quadratic polynomials, there's quartic polynomials, which I think was in the chapter as well. Okay.
So isn't it just basically graphs, sir?
They can be graphed, yes. So it's any function in a variable to the power of n, or any number. So only with variables, though. So for examples, a linear, which is a degree 1. Maybe you saw that in the chapter. So degree is used. So the name of the polynomial, the degree of 1, because it's just something like 2x plus 1. So the power of x is 1. There's a quadratic, which is degree 2, which is our x squared plus 5x plus 6. There's a cubic, which Badai was saying is an x cubed plus 5x squared plus, doesn't necessarily have to have, it just has a cube in it, squared in it, x to the power 1 in it. Doesn't necessarily have to have all the terms. For instance, a cubic equation can just be x cubed. Quartic is where we leave it, is x to the 4. Generally, it doesn't go beyond this, but there are some quartic equations that we look at, and you can get further than this, especially when you're dealing with, if you remember the binomial theorem, which came up with x to the power of 10s and 12s and stuff. But generally, when you're dealing with graphs and stuff, we don't go further than quartic, which would be, this would be an example. It's quite large. Okay. So polynomials have things called zeros. A zero of a polynomial is the value for the variable, for x, which makes the polynomial 0. So if I have a polynomial, 2x plus 1, no equal sign, no nothing. What's the 0 of this polynomial? Well, if I replace x with a half, negative a half, I will get a 0, because 2 times negative a half is negative 1, minus 1 plus 1 gives 0, so that is a 0. So the 0 of this is negative a half. which is very, very similar to the root. The root are the solutions. When it's an equation equals to whatever. So if 2x plus 1 was equal to 0 from the start, you could solve it from that point. And that is usually the way of getting zeros. You solve it and find the roots, because the roots and the zeros are pretty much are not the same thing, because the roots will only be when y is equal to 0. The zeros will be including those complex ones, where you can put in a complex number and you get equal to 0, but it's not necessarily a root, because a root is planted on this x-axis. And that's the difference between the two. So the question is a 0 always a root? Or always intercept the x-axis? And the answer is no. Because, for instance, if our polynomial was x squared plus 1, straight away, x squared, if you let that equals 0, you get x squared is equal to minus 1, and that's the square root of minus 1, plus and minus, and that is not on this real x-axis. It's just not there. It's going to be hovering somewhere up here. It'll be on the imaginary, but that's so. But it's not on the real. It's not real. It's not a root, but it is a 0. It does give you 0 out, but it does not. You cannot plot it, and it does not cross the x-axis. So a 0 and a root are slightly different. You can pretty much you find them the same way, but you just got to be aware that 0 is slightly different than a root. All right.
So basically, fundamentally, a root is just an answer to an equation, yeah? It doesn't have to be...
A root is specifically where it crosses the x-axis.
Oh, yeah, okay.
The answer to the equation when y equals 0, yeah. As 0 can give you out 0 if you sub it in, but will not be on the x-axis. Not necessarily. It could be, but not necessarily. For instance, this example, it was, because you get the same answer out here. Whereas this example, square root of negative 1 is I, and that is not a root then.
Oh, so it's not a root if it has an answer of I?
It's a complex root, but it's not a root on the x. It's not an x-intercept, no.
Oh, yeah, because it's an imaginary number.
Yeah, complex, yeah. Okay. All right. So let's look at a question. Find all the real cubic polynomials with zeros, a half, and 3 plus or minus 3 plus or minus 2i. Okay. So you can see there we've given 3 zeros, a half, minus 3 plus 2i, and minus 3 minus 2i. So we know that it only crosses the x-axis at one point, and the other two zeros are not on the x-axis, because you can see that they are imaginary here. Now, how do I form a cubic equation given all its zeros? Well, one way I could do it is using our old friend, the sum and product of roots. If a 0 is a half, I know that then that can translate into, well, if x equals a half, I know that. If a 0 is a half, that means that 2x is equal to 1, and that means that 2x minus 1 is, I'm working backwards from the way we usually do it, is definitely a linear factor of this cubic equation. Now, hopefully that makes sense to you because you've done this chapter, and if a linear factor means it would divide in evenly, yeah? Okay, so we have 2x minus 1. Now we have the other two roots, and we know those two roots, in order for it to be a polynomial, must be a quadratic. A linear times a quadratic, because two linears multiplied by each other give a quadratic. Hopefully that Makes sense. So if I have this and times another linear, if I take a sidebar here, x plus 3 is linear, x plus 2 is linear. If you multiply them together, you get that quadratic equation. So same here. These two are going to be x equals to minus 3 plus not root 2, 2i, and x is equal to minus 3 minus 2i. So the two same as this. But now that we proved on the previous page about alpha and beta, alpha plus beta and alpha beta, sum and product of the roots, we can use that to form our quadratic. The quadratic is going to be x squared, maybe something x squared, plus something x, plus or minus something at the end. Now, if I use sum and product of the roots, alpha beta is going to get me the c here over c, and the alpha plus beta is going to get us b, I think. All right, so when I do alpha plus beta is probably the easiest one. If you remember from above, if I add these two together, the i's are going to cancel each other out, and I'm going to get minus 6, minus 3, minus 3. Hopefully that makes sense. Now, does that mean that this 6 is plus or minus? So 6 will go in here in the b position. Remember, that's b over a. It's actually minus b over a, isn't it? So that's actually going to need to be, is it minus 6 or plus 6? I'm scribbling out my sign. You tell me. There only is two answers. Minus?
Yeah.
Sure. Let's put it in as a minus. Then redo it as minus b over a. Will give us the product, the sum of the roots. It is minus b over a. So I have minus 6 as b. So that's going to be minus 6 over 1, which gives plus 6, which is not right.
Yeah.
Sir?
Yes.
How did you get for alpha plus beta it's c over a, right?
Alpha beta is c over a. I'm doing alpha plus beta is b minus.
I mean, yeah.
So, I haven't done alpha beta yet.
How did you get the quadratic on the left-hand side again for x plus 3 and x plus 2?
That was an example.
Oh, so then how did you get values for a negative b or for b and a? Because they only give us zeros, right?
Yeah. But as we did in this example, those zeros will fit for product and sum of roots.
Okay.
It won't be on the x-axis, but they'll still work for product and sum of roots, like we showed over here with the 4 and the minus 2 for this one.
So you used what values of b and a did you use?
Well, I used these two. There's two roots. I've already used this 0 to form a linear.
Right, to make it 0, yes. Understand that.
Okay, that's a linear factor. That's the 0. You turn it into a linear factor. The other two, when they multiply, and that's what this was about, when they multiply, they'll form a quadratic.
Oh, okay.
Now you could, it'll be messy, but you could just multiply them like this. You could do x minus root 3 plus 2i times x minus root minus 2i. You could multiply them out like that and form the quadratic the long way, no problem. But I'm just getting used to using sum and product as roots, Rigel's favorite thing. C over A. Yeah.
So x equals negative 3 plus or minus 2i. That's just the two other roots, right?
Yeah.
Okay, yeah.
So there's two more. We just got to form the polynomial out of it. C over A is these two times each other. It's alpha plus beta. This will give us C. times by each other. Now, we did this on the other side the long way. I'm going to do it the short way because it is difference of two squares. The first two are going to be multiplied by each other. Minus 3 times minus 3 gives me plus 9. And the middle two terms are going to cancel each other out because you got plus, you're going to be plus 6i minus 6i, so they cancel out. So we're just looking at the last two terms multiplied, and that's going to be minus 4i squared. Now, minus 4i squared, I squared is minus 1. So that's minus 4 times minus 1, which is plus 4 plus 9 is 13. And that is the product of the roots. So it goes in here.
So this will lead into the other kind of sum and product of roots, right?
The other kind?
Well, when we use like this, like a to the n, or not just cubic.
Oh, yeah, they're directly linked. Yeah.
Okay.
Sure.
Yes.
I'm still a bit confused with when you do a plus beta and a alpha times beta. Like,
Yep.
How did you get values for b and a?
Well, I know when I do alpha beta, it is c over a in a quadratic. Remember,
Right.
quadratic, I'm running out of space here. A quadratic can be written ax squared plus bx,
Yeah, bx plus c.
plus c. And I know that if I have the roots, alpha plus beta will be minus b over a. Now, in this case, I got minus 6, which is minus 6 over 1, if you wish. So that's why I can put in the 6
Yeah,
here.
but how did you? I don't see like.
You don't
like
see how I got minus 6?
Yeah.
Minus 3 plus 2i is one root,
Right.
plus the other root. Minus 3 minus 2i, the second root. Added together, which I did quickly, but I'll do slowly again. Plus minus 3 is minus 3.
Oh, okay.
Minus is
Yeah.
minus 2.
Yeah.
Minus 2i, they cancel. Minus 3 is minus 6.
So you're kind of just using. So half is a, right? For when x equals half, is that a? Like ABC for the quadratic equation?
No, it's not. No, that's the linear. That's the linear bit. What I'm going to do is I'm multiplying the linear by a quadratic to form a cubic.
Yeah. Okay.
The linear bit's easy because it's just x is equal to a half.
Yeah, of course.
And I need to find the quadratic, which is difficult. But I use alpha and beta.
Okay, so if you're given if you're given two roots, you can just use alpha and beta to figure out.
Form a quadratic, yeah.
Okay. Now I understand. Yeah.
Okay. Nearly finished now. If you want to form the actual cubic function, I need to multiply this all out. 2x times that, which you can do, minus 1 times that. I presume you can do that. I'm going to do this really quickly just to get it out of the way. One interesting thing is I already can predict at this stage, at any stage, what the coefficient of the x cubed term and what the constant is going to be. I already know the constant is going to be minus 13, because minus 1 times minus 13. And I know that the cubic is not 2, it's going to be 2 times x cubed. We'll look at that very quickly in a second. But I'm just going to multiply this out. Do stop me if I'm moving too fast. I'm just multiplying by 2x first, and then I'm going to multiply by the minus 1, which is just going to change the sign of that second bracket. And then I'm going to combine like terms, so hopefully you're well able to do this. Plus 11x squared plus 20x minus 13 is our cubic equation. So I multiply a linear by a quadratic, I get a cubic. If I multiply a cubic by a linear, I would get a quartic. The next one up, x to the power of 4. Now, interestingly enough, and this will be a very useful tool, if I have new question. This is not a new question, just a new example. if I have a cubic split up into its linear factors, so this one would have 3 roots all on the x-axis, because you can see that there's no complex numbers in here. So that's sweet. No, nothing off the x-axis. But I can also know the coefficient of the x cubed straight away. What's the coefficient of the x cubed? Be 6, yeah, because x times 2x times 3x will be the only thing that gives me an x cubed. So I know there's going to be 6x cubed at the start, yada, yada, yada. Not sure what's in the middle, but I do also know the constant term at the end, which will be
-2.
-2, which would be all the constant terms multiplied when they're finally multiplied together. It's the only term that would be without an x, because all the other ones will have x in them. Now, the middle terms will be a little trickier, of course, because there's x squareds combined and x's combined, but I can always find the first and the last quite quickly in a cubic or any equation if it's set up like this. Okay, that's just a side note there. Okay, let's do another example question. So we're sticking with our polynomials. Not going to quite delve into division just yet. Not ready for division, but we'll keep going. Let's get rid of that page and start another one. Another question. This one, if you want to do it quicker than me, go for it. So perhaps you feel like you have it down. 2x plus 3 and x minus 1 are factors of 2x to the 4 plus ax cubed minus 3x squared plus bx plus 3. So we're given some factors, they're linear factors, of a quartic x to the 4. All right, we want to find, this is the question, find a and b and all zeros, which kind of hints at the fact that the other 2 factors, there will be 4 linear factors because it's quartic. The other 2 are going to be off the x-axis. They're going to be complex. Now, if you want to go and do that quicker than me, go for it. I'm going to go through it now. Answer. Okay. I'm going to use a very similar method to the last time. 2x plus 3 times x plus 1 times, what type of equation is it going to be timesed by, multiplied by, not timesed?
Quadratic.
Quadratic, yeah.
It's going to be a quadratic, because you got a linear, it's going to be a quadratic then. So, I'm going to say x squared is definitely there at the start of the quadratic, and I'm going to say minus 1 is definitely there at the end of the quadratic. Are you comfortable with that? How I got that giant leap?
Yep.
I did it because I know 2x by x by something has to be this first term. 2x to the 4. And there's already a 2 here. So 2x by x gives 2x squared. And times another just x squared gives 2x to the 4. And the same thing for the constant number at the end. 3 times minus 1 is minus 3. And minus 3 times what will give us this last term? And it's minus 1. Minus 3 times minus 1 gives plus 3. So I know that these 2 terms are solid here in our quadratic. What I don't know is the middle term, which I'm going to call a new variable, c. Okay, so now I need to find a, b, and c. But at least I'm closer than I was when I started the question. Okay, I can combine these 2 into a quadratic if I want. 2x squared. I'm going to have a minus 2x plus 3x. So that can be plus just x, I think. And I'm going to have a minus 3. So that's just multiplying that out. If you need to do that slower, you can. Okay, this times this gives that. I know that for sure. So I might as well do this times this and equate it to that. I know 2x4 is at the front from this times that. And then I need to multiply and tidy up. So I'm going to multiply out this quite quickly. 2x squared times that. Now I'm going to multiply by x. Now I'm going to multiply with minus 3. Well, happy enough so far because I have a 2x to the 4 and a plus 3 at the end, which is what I want. These middle terms combine my like terms. So 2x to the 4. Let's look at what is going to be with the x cubed. I'm just going to put them all in brackets and x cubed outside. 2c plus 1. That's it. It's x cubed. All right, and now I'm going to look at the x squared terms. Minus 2 here, plus c, minus 3. And then I'm just going to look at the x terms. Minus 1, minus 3c. Plus 3 at the end. Okay. Now, this is the same as that. Let's start a new page for this. Which means that this term has to be the same as this term. Which means I can jump to the conclusion then that a equals 2c's plus 1 from the x cubed. I can also say that this has to equal negative 3 from the x squareds. Just looking at the coefficient. So that's c actually minus 5 if I combine those. And that's minus 3 from the question is equal to c minus 5. From the x, up here I have a b. Not plus b, I'll just put in b. Minus 1 minus 3c. Okay. So what I have here are 3 equations, 3 unknowns, a, b, and c, and I can just solve them. Oh. Oops, low battery. I can just solve them. 3 equations, 3 unknowns. This one, c, is going to be, so this is the easiest one because there's only c in it. C is going to be, add 5 to both sides, you get 2. C is 2, yes. Awesome. A then is going to be, well, if I know C is 2, A is going to be 2 times 2 plus 1. A is going to be 5. Amazing. And B then is going to be minus 1 times minus 3 times, not 2. C is 2. So B then is going to be minus 7. Awesome. We have A, B, and C. Do I have my...
Sure, for
yeah.
B?
Yeah.
You took the part out of negative 2 plus c minus 3, right?
For B, for this one?
Oh, sorry, for x squared.
Yeah. Yeah.
You took it out of negative 2 plus c minus 3.
Yeah.
How is it minus 3 equals minus c minus 5?
C, take away
Yeah.
3, take away 2, is C, take away 5, yeah?
Yeah.
Which is this bit. The question, x squared coefficient is negative 3. So I took this bit, negative 3, and let it equal this bit. Because they're both the same. They're both coefficients of x squared.
Oh, so you just let that equal -3, I guess, right?
Yes.
Okay.
Okay. Is my question complete? No. Find A and B, done. Why did I even bother finding C? Well, C is going to help us find the zeros, because now I have this quadratic as well. My quadratic factor is x squared plus 2x now, instead of C, minus 1. Awesome. If I manage to solve this out and get it zeros, I will have my final zeros of the function. Okay. Already, I know it's going to be complex because they use zeros in the question. So I'm going to just go straight to my formula, let it equal 0, and then use my formula, minus b plus or minus the square root of b squared minus 4ac minus 4ac b squared minus 4 times 1 times 1. Oh, that's going to be plus 4, is it? That doesn't seem right. What have I done wrong? B squared is 4 minus 4 times 1 is 4. Take away that. I think it's right. Is it 4 plus 4 plus 4? I think so. Okay. Now we have over 2 times is going to be over 2 times 1 is 2. I think that's right. Correct me if I'm wrong. X is minus 2 plus or minus root 8 over 2. Okay, we're not actually going to get a complex number, but we'll get a surd. That's cool. That's going to be minus 2 plus or minus. That's going to split up into root 4 times root 2. Remember, root 8 is root 4 times root 2, which is going to be 2 root 2. 2 root 2 all over 2. That's pretty much it. You can just divide everything by 2, and you get minus 1 plus or minus root 2. Okay. Which is irrational, and they fooled me. They are roots. They are real, but they are surds. Okay. So yeah, I think that's the answer anyway. I can't see a mistake if it's not. Okay. So that is all the roots or zeros for the equation. They're all on the real axis. That's cool. 2 of them were given in the question. 2x plus 3, which gives me the root x is equal to -3 over 2. That's one root. We have x minus 1. This is once again given in the question. Oh, I'm just a little bit off screen here. These are given in the question, so I got here they were. That means x is equal to 1 is a 0. Another 0 then we have from here, x is equal to minus 1 plus root 2, and our last 0 is x is equal to minus 1 minus root 2. Accordingly, you could have just wrote plus minus like I did here. But there are our 4 zeros of my quartic polynomial, and that's the answer.
So is there a way that you can figure out if there is a complex number, unless the question told you so?
If there is a complex one?
Yeah.
Yeah, the graph it.
Oh, okay.
It's probably the easiest way. Yeah.
Oh.
You can more than likely, there's more in the world of maths that have complex zeros than have, because it's very rare, especially for a quartic. Well, maybe not for a quartic, but if you go to the 5th one or a cubic one, it's rare enough that all 3, or all 5 would be on across the x-axis.
Sir?
Yeah.
I understand everything except for when you started to solve for A, B, and C, when you expanded the 2 quadratics.
Here?
At the top, yeah, right there. Yeah.
Coefficients. I equated coefficients of the question. So the question gave us the coefficients. 2x for ax minus 3 plus bx plus 3. And then when I did out, so that's the whole crux of the question. You let the coefficients equal the coefficients. When I multiplied out what I found, I let the coefficients equal the coefficients. So 2c plus 1 here equals the coefficient of x cubed up here, a. 2c plus 1 equals a.
Right. You let c equal 2, right?
Oh, it didn't. I found c to be 2, yeah. Because the coefficient of the x squared was minus 2 plus c minus 3. Now, I shortened that to c take away 5.
Sorry?
That is c minus 5. Yeah?
Yeah.
And that equals minus 3, which is the coefficient of x squared.
Minus 3 is the
Yes,
coefficient of
yes.
x squared, right?
They're the x squared coefficients. I've let them equal each other. And same for x. Rewatch the video. I'll try and put this up on YouTube. Rewatch the video again if you want to go through that one again.
Okay. Also, how is it? Why did you do it from like A, C, B instead of like A, B, C? How come you solved for C before B?
That was my choice. It was easier. This is the only one with one variable. These two other ones have 2 variables. That was logic.
Oh, and then for C, right? But yeah, I understand for when you say the coefficient of x is equal to C, right?
No, the coefficient x squared from the question is minus 3. When I worked it out, I used C. I came up with C. When I worked it out, I got this as my coefficient of x squared. Now they have to be equal because I use the same information.
Right. So
I think you should watch this whole thing again because I think you missed the entire point of the whole question.
Okay.
Watch it again when I put it up. Okay. Or maybe go through it, Mr. G'day, point out the question to him, and he maybe can go through it again. But I'd have to start the question again in order to explain it all again. All right.
Yeah, I'll just watch the video.
Yeah, I think watch it back. Yeah. We don't have much time left, so I just want to get to it a little bit more.
Yeah, it's fine.
Okay. Let's look at division. Okay, so division of polynomials. So same as division of fractions. If I have a fraction and I want to turn it into its, turn it from a mixed, or turn it from an improper fraction into a mixed fraction, well, what would I do? I would do 10 divided by 4. 4 fits into 1, doesn't go, okay, 4 fits into 10 twice, and then there's going to be a remainder of 2. Okay, so I could write that then 2 plus a remainder of 2 divided by the original 4, which is just, and I could simplify that into 2 plus a half, if I want to write it like that. So although it didn't go in evenly, I can divide it in and get some sort of remainder and then put it over whatever the divisor was. That could also be written a number of different ways. You can combine it again if you want. You can multiply 2 times 2 to give 5, or 4 plus the 1 is 5. That's 5 over 2. You can put it back together, and that's essentially the same system as dividing by polynomials, especially if it doesn't go in evenly. This requires some long division. Let's look at one. Find the quotient and remainder. So the quotient and remainder of this division. X to the 4 plus 4x cubed minus x plus 1 all over x squared minus x plus 1. So I hope that you looked at long division using polynomials during your work for the last week. If not, well, I'll go through now quite quickly. So let's set up a division. Minus x plus 1 divided into x to the 4 plus 4x cubed. Now, my question didn't have an x squared term in it. Do I include an x squared term in the division? Yes, I do. I fill it out fully. Because it's going to divide into each term. There is an x squared in the divisor. I'm going to put 0x squared. There's no x squareds. Fill it out into it's full terms. Plus 1. So I just put in a 0x squared into what I'm dividing the numerator, if you wish. Okay. So we only look at the first term. How does x squared divide into x to the power of 4? Well, it goes in x squared times. How do I know that? Well, because x squared times x squared gives x4. And I can write that underneath. X squared times x squared gives x4. But I must also multiply x squared by all these other terms as well to fill out these spots here and get my next division. X squared times minus 1 gives minus x cubed. No, sorry, minus x. X squared times minus x gives minus x cubed. X squared times 1 gives plus x squared, or plus 1x squared. Okay, so I've just multiplied x squared by these three terms, which are dividing it. Okay, draw a line. So this is like long division from when you did it maybe in primary school or year 7 or 8. It's just a little bit trickier. Instead of different units and decimal points, maybe you're dealing with variables and x's. And I've got no battery again. Hopefully it won't run out. Okay.
Sir, wait, is this supposed to be x3 because x squared plus times x is x3,
right? Where? Here? That is x3.
Oh, you didn't put plus 1 yet on the left-hand side. Okay, wait, sorry.
Okay. All right, so now, like you do in long division, you subtract everything here. So change the signs if you want to say that. So I've changed all the signs. x4, take away x4, disappears. Wonderful. You have 0 x4s now. 4x cubed plus x cubed gives 5x cubed. 0x squared, take away x squared gives minus x squared. Now we bring down the next term because there's 3 terms here. That means I have to divide into 3 terms. Now I restart my process. X squared times what gives this first term? I think it's a plus 5x. 5x, let's check that. So that 5x has to be multiplied by all these 3, and that pops into 1, 2, 3 positions. 5x times this gives 5x cubed, which is what I want. So that's the check done. If these two are the same, you're in business. 5x times minus x is minus 5x squared. 5x times plus 1 gives plus 5x. Draw a line, change the signs. Cancels, wonderful. Minus x squared plus 5x squared gives 4x squareds. Minus x minus 5x gives minus 6x. Pull down the last term, 1. We got to do one more division. And of course, it makes sense that we do one more. A quadratic multiplied by a quadratic will give a quartic. Okay. And because there's a constant term here, we need to have a constant term up here. All right, so last thing, looking at the x squared again. X squared times what gives this 4x squared? So it's just 4, isn't it? I think it's just 4. Plus 4. Let's check that by multiplying each term. Plus 4 times that. 4x squared. Plus 4 times. This is like reverse. You're multiplying this times this to fit it to this. And then you're going to figure out, is there a remainder? So same as way you could multiply 4 times 2 to give 8, and then you see there's a remainder of 2 from that. And it's pretty much the same system. It's just a bit more complicated. 4 times minus x gives minus 4x, and 4 times plus 1 gives plus 4. Draw a line underneath. Change the signs because we're going to subtract. Minus 2x plus 1 minus 3. Uh-oh. Well, not uh-oh. That is just our remainder. So it doesn't divide in evenly. It gets pretty close, but there is
It's not a factor, right, sir? It has to be a 0 for it to be a factor.
Yeah, it has to be a 0. So that's your remainder theorem. If you subbed it in, it'd have to be 0 in a way, but we haven't done that yet, and that's possibly what we're going to do tomorrow. So we have a remainder. How do we write our answer then? Well, we can write it a number of ways. We know that if I multiply x squared plus 5x plus 4, which is this, if I multiply that by this, x squared minus x plus 1, I'm going to be this much off the answer. There's going to be this much left behind, which I can just put in here. And I can write it like that, or I can put this, this as x squared plus 5x plus 4, and I can do minus 2x minus 3 all divided by x squared minus x plus 1, which is a bit more messy. I can write it like that either. But that's the answer. So we got a quotient. That's called a quotient. Or this is called the divisor. As you divide it in by, it's called the divisor, and this is called the remainder, which you know already. Often called OR of x, not often, sometimes. This is called Q of x, and this is just a divisor, it doesn't need. So the quotient will be, so when I divide 4 into 10, the quotient was 2, and the remainder was 2. Hopefully that followed. Now we've kind of run out of time for today. So I'll post this whole video up. If you want to watch it again, it might be a good idea. If you have time, I don't know if you really will or not before tomorrow, but that's okay if you don't. We will look at remainder theorem, factor theorem. What else is on? Looking at the graphs then of cubics in general. What else have we got on tomorrow? A little bit more at the sum and product of roots of any polynomial, which I think Rigel you were talking about there a second ago. That's on that's in your book towards the end of that chapter as well. And we're going to look at that's it, is it? Yeah, that's pretty much it. So we're going to look at all those things. Hopefully, finish off the theory. Now that's a brush over the theory, not an in-depth look at the theory. You guys got to go through. So I've pretty much done the chapter up to, let's have a look at the chapter here. Up to around page 125. So I've done up to page 125 of the chapter. Around there, we're going to pick it up there with the remainder and factor theorem, which is kind of just from this, which isn't too bad tomorrow. And hopefully we get most of the rest of the chapter finished between tomorrow and Thursday. Or if not, we should get all finished by Thursday. And then we'll move on. But my goal for you guys is, if you have time, either watch this video again or get into those questions up to page 125, just to have a little look at some of the questions, see can you do them. I'm not going to set any specific homework because I don't know how much time you have tonight. Okay?
Yeah, sir, is it okay if I were just to understand the previous question that I asked for the video?
So, what? Rigel and Badai, if you don't have questions, or Rigel and Dustin, if you don't have questions, you can leave now. You probably have lessons soon. Badai, I can answer your question now.
Okay.
Okay. Bye, sir.
Okay,
Thank you, sir. Goodbye.
Yeah, I was just asking, page 125, is that